So, now we will talk about the 11th lecture on module 1, where we will solve some numerical examples on single degree of freedom system, also help you how to write the equation of motion for multi degree freedom system using different techniques. Just for the benefit of all the readers, let us quickly summarize what we have done so far in about few minutes. We started with a matrix of presence of mass, presence of restoring component K, presence of the damping force which is dissipating component, and the external agency or the external force. We said that in all cases mass must be present and restoring component should be present. There are two reasons for this. One, mass is always present in an offshore platform because essentially in the initial conceptual design it was actually gravity based platforms. Subsequently, the top side details are so massive, therefore, mass presence will be always obviously there in all type of structural systems. And generally offshore platforms are designed in such a manner that one must get a very commandable restoration capacity or recentering possibility should be there, be it gravity based platform, be it jacket platform, be it compliant system, even be it semi submersible, one must ensure that there is a proper recentering, so that the displacements or the vibrations given to the connecting elements like umbilical cables, pipelines are minimized, so that exploration and production can happen conveniently. So, K will be always present in the system. Now, one can always ignore the dissipation of energy or the response because of damping. The damping is always present by two external sources. One can be aerodynamic or air, presence of air will also cause damping. The second could be hydrodynamic, which are obviously and inadvertently present in offshore system, but for hypothetical consideration we can neglect them. To find out the essential characteristics of a single degree freedom system model, we may sometimes ignore the external force also. We call this as undamped, because damping is not present, free vibration, because f of t is 0. Similarly, we moved on to the presence of mass and presence of K. We never wanted f of t, whether damping may be present, we call this as damp free. Subsequently, m and k are present, damping is not present, but f of t is considered, we can call this as undamped forced vibration, and of course, in the last case all are present. So, we can call this as damped forced vibration. Now, we have seen the response behavior of all these categories separately in a closed form solution, which is derived analytically from the basic spring mass model, which we have established as one of the standard models for representing a single degree freedom system. So, for understanding, let us quickly write those equations back again for recollection. Let us see that can I write all these equations of all the systems back. Quickly recollect that how the response were different in different segments, where the transient response was focused, where the steady state response was focused, what is the upper bound of the response, at resonance what happens system. We have discussed this for the past 10 lectures. Let us quickly summarize this in few minutes and write down the equations, because one can understand this lecture as a summary lecture of all the 10. Even if you miss some of the earlier lectures, even with this lecture you will be able to understand, yes, these are my equations, these are my closed form solution, you can always derive it back from the fundamental. So, with that principle, let us write down this equation. I will call this as, let us say, case 1, case 2, case 3 and case 4. Of course, in case 3, when I have forced vibration, there will be one more subdivision in this. The subdivision is, if the forcing frequency is matching the natural frequency, then the behavior is different. Similarly, in the case 4, I will again have a subdivision. If the forcing frequency is matching with the excitation frequency or the natural frequency, then I have a different case. Similarly, when C is present, I can have underdamped, critical and overdamped. All the subdivisions will anyway play a role. We have done all of them. Let us see quickly how they can be written. So, I will say case 1, just for understanding purposes, M, K present, C, f of t absent, just for our understanding. That is case 1. So, we know that the response is given by x naught cos omega n t plus x naught 0 by omega n sin omega n t. Then let us say case 2 where m, k are anyway present, c is present, but f of t is absent. The moment we said damp, there are two damping we studied. One is the Coulomb damping, which is frictional model. The other one is the viscous damping, which is proportional to the velocity. In our case, we already defended that why viscous damping is applicable to offshore structures, because of very important reason that offshore structures generally in the presence of water. Therefore, viscous damping or the damping proportional to velocity of the water particle will be a better assumption considering the Coulomb damping. We have also technically and analytically proved that viscous damping has got more deceleration or more recentering capability compared to Coulomb damping, because Coulomb damping is the number of cycles taken in case of critical damping, where C is CR is equal to CR, which is purely hypothetical. We said x of t is given by a plus bt of e to the power of minus CCR by 2m of t, where a and b are constants which can be evaluated, and CCR is the critical damping, which is 2m omega n, and for underdamped system we express damping as a ratio which is C by Cc, which is expressed as zeta, always in percentage. So, x of t was given by e to the power of minus zeta omega n t x 0 cos omega dt plus where omega d is called damped vibration frequency, which is function of zeta omega n 1 minus zeta square, where zeta is the damping ratio. And we have already seen that the response typically will decay x of t, okay, omega x of t, that is a time, typically it will decay. This is decaying because there is an exponential negative sign here, so it decays. Once we say it is decaying, then the ratio between the successive amplitudes, let us say I want to know the ratio between the successive positive amplitude or the successive negative amplitude, I will call this as logarithmic decrement. We derive this equation, we can write the equation here. The logarithmic decrement, this logarithm is a Napier's logarithm, base e, it is not natural logarithm, I mean this is not log to the base 10. So, logarithmic decrement is given by 2 pi zeta by 1 minus zeta square. If you want to make it more general, then I should say zeta can be given by 2 pi m x n by x n plus m minus 1. where m is the number of successive frequency peaks either in positive or negative, and n is the first point what you are starting. You can start at x naught, you can start at x1, etc. Okay. So, one can find zeta, and zeta will be expressed in percentage, because zeta is generally given in percentage. Then we move on to forced vibration, that is 3. So, undamped, let us say case 3, I say m and k are present, c absent, but f of t present. Now, there are two cases here. F of t is considered to be a general function of p0 sin omega t, where omega is called the forcing frequency. Now, the case can be either omega equals omega n, the natural frequency of the system, or omega less than or greater than omega n. It is not equal to omega n. Of course, here also in equation of motion we know that omega n is root k by m. So, we know this. So, there are two cases where this can be 1 and this can be 2. So, we will write the equation for both of them, because both equations are different. So, let us write down for this where it is not equal. So, x of t is given by x0 cos omega n t plus x naught 0 by omega n minus p 0 by k omega by omega n by 1 minus square of sin omega n t plus p 0 by k 1 by 1 minus omega by omega n the whole square of sin omega t. Now, this omega is the forcing function frequency, and this omega n or the natural frequency system given by this equation for a single degree. And we already said that the response contains two parts. One set of the response depends on the initial condition given to the problem. We call this as transient response. The other does not depend on initial condition. We call this as steady state response, which will always be present. So, for our interest we generally consider steady state, but I already told you in ocean structures sometimes transient response is also important. The specific application of this will be discussed in the next module, where we call springing and ringing responses. So, it is also important, we cannot simply, because we very well understand in case of the natural frequency matching with the excitation frequency, the development of response, though it is gradual, it becomes bounded or it gets unbounded. So, the growth is there. So, when this growth can damage the system, we need not have to ignore that part. So, we are interested in focusing on transient response also. For the time being, we will focus only on the steady state response in general. Okay. This is what we have discussed as far as x of t in this case concerned. Now, when omega equals omega n, you will obviously see the denominator becomes 0. You cannot use the same solution back again. So, we said the PA is different, the particular integral is different. Therefore, we gave an equation which ultimately results in what is called deformation response factor RD. So, we made it simplified to understand RD as deformation response factor, which is 1 by mod of 1 by 1 minus omega n the whole square, and we generalized x of t in this case as RD p0 by k by m, no, p0 by k sin omega t minus theta, or let us say phi. And we said this phi value has two values. One will be 0 for omega less than omega n, will be 180 for omega greater than omega n. Now, it is silent when omega equals omega n, it is silent. So, at omega equals omega n, at this specific case x of t at omega equals omega n is given by a different expression now, which is minus p0 by 2k omega n t cos omega n t minus sin omega n t. So, whether I write omega here or omega n t here does not matter, because this is the validity. I want you to kindly check all these equations back from your notes and see that I am writing the same equations back again. And we have seen that when the damping is not present, because we are looking at the undamped case here, when the damping is not present, the response builds up . It builds up, expected to reach infinity after large number of cycles, and we have shown mathematically for every cycle the increment is pi times. Like a bell, it grows like a bell. This undesired behavior we do not want, because I cannot allow the response to remain infinity, because we have no control of this condition in the reality, because the forcing function frequency can match the natural frequency of the system. At that situation, the system should not enter into a undefined unbounded response. We do not want a system to design like that. Therefore, we now consider damping, which is present inherently in the system, which is case 4. So, case 4 is more or less a realistic system where m, k, c and f of t all are present. In C, usually we talk about underdamped case. In f of t, we will talk about both cases, omega equals omega n, sorry, omega equals omega n, both we will talk about. So, we derive this equation, x of t is given by e to the power of minus zeta omega n t a cos omega dt plus b sin omega dt plus c sin omega t plus d cos omega t. Now, one may ask a question here that the response is again in two parts, one on omega d, which is a function of omega n, and other is omega, but again there are constants c and d, constants a and b. It may give a confusion at this stage to people that does response analysis of damped forced vibration depends on initial condition or not. Please understand, the constants c and d are not dependent on initial conditions, they are simply, for our understanding of written c and d, it is a long equation. So, it is nothing but p0 by k 1 minus beta square by root of, sorry, 1 minus beta square plus 2 zeta beta square, whereas d is minus p naught by k. Remember, the negative term in our derivation is associated to cosine. That is how I do the organ diagram. 2 zeta beta by 1 minus beta square plus 2 zeta beta square. So, they are not dependent on initial conditions of x naught and x, whereas a and b, if you open up the transient response, you will see that they will be function of x0 and x dot 0. So, therefore, one can say that this will die down because there is a multiplier of exponential here. It will not die down because it does not have a multiplier of x naught here at all. Most importantly, please understand that the steady state response is nothing but a magnification of a static response. So, there is a factor which magnifies P0 by k, but P0 by k is generally called as static response. So, let us see what is the D factor, what we call dynamic amplification factor. Okay, we made an organ diagram for this and understood D as a resultant of the components of cosine and sine, and we wrote this expression which we already derived in the last lectures. So, the dynamic amplification factor or dynamic magnification factor, please understand the term is amplification is only applied to the static response. Okay. So, you are magnifying the static response. So, is again given by D. Please understand that this D is different from this D. Okay. This actually is some mathematical constant. I have indicated. You can, if you want to avoid confusion, you can even make it as D1 or E, etc. So that this D and what I am writing is as different. Okay. Though the nomenclature may unfortunately remain same. So before writing D, let us say we write omega equals omega n. I want to capture the response. So we already said that x of t, looking only the steady state part, because transient part we are not interested for the time being. The whole response is nothing but E minus zeta omega n t, whether I write omega n or omega does not matter, because this is the validity. The transient response part does not change. It does not change, same, minus P naught by 2 zeta k cos omega n t. That is a generic expression. Okay. I can always generalize this as x of t or x of t as some amplitude sin omega t minus theta. It is always preferable to express the response in terms of some factor of that of forcing function. Okay. The moment we say, then this value rho is given by P naught by k 1 by root of. And we said tan theta is given by it is other way. And we know the angle of theta is the resultant with respect to the axis of sin omega t part. So, from this I can say x of t by x static, which is my ratio of response, which will now give me the dynamic amplification factor. Why? Because you see that the amplitude of the response finally is getting magnified by static response for sometimes. We all know that beta is ratio of the frequencies, and zeta already we know C by Cc, where there is no multiplier here, it is separate. Therefore, the dynamic magnification factor D is given by 1 by root of 1 minus beta square square plus 2 zeta beta square. And we also understood that even at omega equals omega n, the response builds up, no doubt, and it is bound at 1 by 2 zeta. Then we compared both the responses of the bell mouth increasing response of undamped system at resonance, which was not able to capture because the RD plot, if you look at, it was not able to capture at resonance, is unbounded, whereas this captures at resonance because this function is derived at omega equals omega n. And we have discussed both of these and compared them and said how we have understood the response build up in both the cases. Having understood this, the one more small focus which we have to understand here is how to estimate damping experimentally. We have already seen that. For example, if I conduct an experiment and try to measure the displacement of the platform using an LVDT, linear variable differential transformer, or using an accelerometer, then I will get a plot of this order because I give an initial displacement to the system. I can find out the peaks and try to get the value using the equation what we already discussed. I can get zeta from this. There is one more way of getting the damping ratio zeta, which is called half power bandwidth method. To obtain damping ratio zeta. Now we can proudly write we know. If you ask me how did we know, just now for 20 minutes I said we know that. Okay. So, therefore, please look at that. We know x of t is given by some ratio, some amplitude sin omega t minus theta and rho is given by P0 by K . Yeah, we have it here. So, what I do is I pick up this equation, maybe equation 12. If I am just slipping by one number, you can correct me if I am wrong, maybe 11 I cut that to the last lecture, let us say 12. This we know this equation, I want to plot this equation for different forcing frequencies. That is the only variable here, okay, because P0 is the known amplitude of the forcing function, K is the known value because M, K are all known to me. Beta is the ratio of omega versus omega n. Omega n is known to me. For every value of omega, I know beta. I select zeta, which I want, but in this case I do not know. Therefore, what I do is I plot this for different ratios and get a function or a plot like this. If you look at this plot, a typical plot of this will look like a bell. Now, the sharpness, the crest, the width depends on what zeta you assume for plotting. Now, it will certainly give a peak value. Let us say this is my peak value. Now, the plot will have an x axis as the excitation frequency, in hertz, and this will be response amplitude. Which is this, okay, this part, only the amplitude. It will have a peak, okay, I know this value from the plot. Pick up this value and try to mark an horizontal line, I do not know whether you will see it or not, I will mark it in yellow, an horizontal line whose value will be equal to 1 by root 2 of the peak. Okay, pick up this value. Fortunately, it will cut this bell at 2 points. Project those frequencies down, because I will call this as F1, this as F2, F for the frequencies of the forcing function. So, F1, F2 can be now obtained for the horizontal line cutting this curve which has been plotted for equation 11 for an assumed zeta. I want to know what is the zeta, that is the argument here. Okay. You may ask me, sir, you assume a zeta and you are checking the zeta. It is true in this case also. See here, you have got a response, the structure is decaying, the response is decaying, it is decaying at a given zeta. You do not know the zeta, the whole exercise is to capture the zeta. Okay. Here also the same argument, right. So, I want to capture the zeta, I want to know what is the zeta, estimate from this. So, this point are called, these points are called half power band points. Okay. That is why it is called half power bandwidth method. Now, interestingly, if the curve becomes so narrow, and your 1 by root 2 comes here, obviously you will get practically only one f. Okay. That is why it is called bandwidth method. So, you have to design in such a manner that you get a proper bandwidth getting F1 and F2 properly. Okay. Since this dependent on various factors, this method is not accurate. Okay. So, I know F1 and F2, now I want to estimate zeta, let us see how do we do that. We already know the dynamic amplification factor is given by 1 by root of 1 minus beta square square plus 2 zeta beta square. We also know for beta equals 1, what does it mean? Omega equals omega n, because omega by omega n is beta. Substitute, you will see the maximum amplification what you will get from this case at resonance is 1 by 2 zeta. Now, one may ask me why it is called maximum amplification. It is called maximum amplification because this amplification is ascertained at resonance. System is expected to vibrate to its maximum response only at resonance. Therefore, we call this a maximum excitation. That is why we say this is the upper bound of your response. Okay, the 1 by 2 zeta is what we are having. Now, I have two equations. One, x of t is rho something which we wrote, where rho has p0 by k, I call that as x static, with some amplification factor which is root of 1 minus beta square square plus 2 zeta beta square. You can easily understand this equation physically in sense x of t of a given system is nothing but magnification of static response, okay, and that factor is this, right. Now, this can be equal to the maximum value is known to me, okay. I know 1 by root 2 of this. What I am going to do is I am going to substitute these two values considering at these frequencies they are the peak values. Okay. So, if at this frequency if they are the peak values, the excitation will be almost equal to this. So, what I would do here is this value will be also equal to x static of 1 by root 2 of 2 zeta, because that is the maximum response I get for some zeta. And why I am saying x static? We know already very well that x of t is nothing but a magnification of static response. I write in the same manner here, okay. This goes away. You may say why I am equating, this is an analytical constraint. If you really wanted to find out at what zeta this is happening, you have to equate this, okay. We equate this, cross multiply, square them, it will become a quadratic in beta. Okay. So, I will get beta 1, beta 2, two values now. Is it clear? So, with famous mathematical sentence, neglecting higher powers of zeta and solving. Okay? This is very important. You must know how to solve this, right? We write directly beta 1, beta 2, one minus zeta square 1 minus zeta plus zeta square. Sorry, you please change this. This is plus and this is minus. Please make a change here. So, I should say beta 2 minus beta 1 will be 2 zeta. So, I can easily get zeta now as beta 2 minus beta 1 by 2. I expand beta, which is half of omega 2 minus omega 1, but of course, omega n. I can also write instead of omega also half of f1 f2 minus f1 by fn, because I have used f in the previous figure. I can write like this, one and the same. And we all know fn is omega 2 plus omega 1 by 2, because that is the midpoint. Therefore, zeta is half of f2 minus f1 by f2 plus f1. So, if you know these frequency points from the half power bandwidth method, you can easily find zeta by this equation. Okay, this is one method to find zeta. Other method is of course experimental, to conduct experiment and get zeta. Okay. Do you have any doubt till here? Now, it is summarized completely about the single degree freedom system model, starting from equation of motion, explaining all analytical procedures, deriving all equations step by step, summarizing and understanding physically, and relating the understanding to the design of offshore structures. Okay, do not isolate dynamic analysis and design, they have to be integrated. All the time we have been talking about the physical characteristic of a platform in terms of its design. Design is nothing but finding out the geometric form of the platform and the member dimensions and of course, the material. So, if you know them, for a given form, how the dynamic analysis can be integrated with the design, that is what we are looking at now. Okay, never isolate dynamic analysis and design separately, they are integrated. You may study them in two different courses, but you should be able to integrate them at any given thought point of time, you should do it. Okay, now let us do some couple of problems to understand how so far the equations developed and generated and understood and by hearted and rewritten can be applied in numerical problems. This is very important, because that is how you will realize how mathematics can be understood, because if you do not see the numbers, if you see only zeta, beta, x naught, x dot, you will not appreciate. Once you see the numbers, you will know how they can be, because numbers will have unit conversion. Let us see them. To start with, we will take up a simple problem writing equation of motion for multiple degree freedom system models, because we have written equation of motion using only one mass and one spring system. Let us deal with couple of them and see how we can write equation of motion. So, I will take up an example 1. Let us say the system is like this. Let us put two mass points, and to prevent the mass from oscillating in the vertical axis or the vertical plane of the board, I have to put a constraint to this mass. Let the mass rest on roller. Why rollers? rollers will offer no friction to the mass on this plane, and roller also prevents mass from oscillating the vertical plane. The mass, if at all, can move, only move in this direction. One can ask a critical question. The critical question is like this: view the system from here. Now you are viewing the system from here. The mass cannot move vertical, fine. The mass cannot move, can move horizontal, fine. But view from here, I will draw the figure like this. This is my mass. These are my wheels. Just to differentiate the wheel in elevation and plan, I am doing like this. It is not that it is oblique wheels. Okay. Now you may have a question: when I pull the mass, will the mass move in this direction? Then it is not a single degree. Okay. So I put an artificial constraint here, which is assumed that the mass does not move normal to the plane also. Okay. Now the mass has only one freedom. Each mass has different freedom. Now why? Why? Because the stiffness of the springs are different. If the stiffness are same, what will happen? Even then the mass can be different. Even if the mass is same and stiffness are same, will it have a single displacement? No, because the force offered from one point, transfer of the force to this mass will have different mechanism. Therefore, x1 and x2 will be different. Now let us come back to degrees of freedom. Degrees of freedom are not those points where the mass is lumped. Degrees of freedom are those points or independent coordinates which will needed to require the position of mass or configure the position of mass at a given instant of time. So at any given instant of time, mass m1 and m2 will be located independently, though they are connected with spring K2 as well as they are totally connected by spring K1 to the support system. So you need two coordinates independently to locate m1 and m2, they cannot be connected, therefore it is a 2 degree freedom system. Okay. So I am not putting a dash part here, we will put a dash part in the next problem. So I want to write equation of motion, so it is very easy. Let us follow this principle easily and you can write equation of motion comfortably. I will use Newton's law. There are many methods. I will also solve the same problem using energy principle. I will write equation of motion in the same manner. You will see both methods will give you the same equations of motion. So this is my first mass point, I call m1. We know that if at all I want to set a motion, I must give either a displacement or a force. Okay. The moment I pull this mass, please listen carefully, this is very important. This is the point where generally people get completely confused. Okay. So they adopt two techniques. One, without understanding whether this is x1 or this is x2, without understanding this is m1 or m2, they have a blind argument. They will write a mass matrix and stiffness matrix immediately without knowing the problem. It means they are by hearting, okay, which is very wrong and very bad. If both k's are equal and both m's are equal, they are really gone, because by heart will not help. The second issue is which value will be negative and positive. So therefore, you will not be able to remember at the age of 30 till 30 you can remember. When you cross 50 you will not remember. If your fundamentals are not clear, you cannot remember at all every time you turn the book, and unfortunately, and which is the truth, every author explains writing equation of motion in his own style. Ultimately the equation of motion will be same for all authors, but the explanation given by authors are actually confusing. Okay, so the best mechanism to avoid this confusion is follow one author so that you get confused in the same manner as he is confused, so that you follow the same path. So the one author which you will get confused will be me, so follow this. So I tell you a very short technique how to remember this, that is very important. If you remember this, I think you will not make mistake. When I pull this mass to the right, that is what my displacement is, this spring will try to pull it back. So let us mark it here. Now I am interested in writing out the force. We know spring has got a stiffness value which is force per displacement. If I really wanted to find the force, I must multiply the displacement with the spring constant. I get the force. I am writing force equation, that is what Newton's law is. Okay. So stiffness multiplied by the displacement will give me the force. To make the problem more interesting, what I will do is I will not say k1 and k2, let us change these values slightly. It is not because I have an answer here, it is 2k and k, let us make it like this. Let the mass be both m. Now, this spring, when you try to move to the right, they will get compressed. You will offer a force in the opposite direction. So, let us do that force in the opposite direction as stiffness of the spring. So, I write here 2, okay, write here 2, I have replaced it. So, multiply the stiffness of the spring with that of, identify the coordinate where you are starting the equation, write that coordinate first and then the next coordinate second, okay, x1 minus x2. Similarly, for the second mass m, I try to move the mass towards right. You may ask me, why sir always right? Because the boss is always right, okay. In this case, I am having the displacement to the right. So, I move it to the right, the mass will move to the right. This spring will not allow the mass to move because recentering concept. The spring will try to pull it back and I want to find the force, multiply with the constant of the spring, and now same argument. First write the equation where you are writing and then the coordinate of the next. Okay. So, I want to write Newton's law, force is mass and acceleration, because the displacement is x1, therefore, x1 dot will be my acceleration, second derivative of displacement, which will be given by minus 2k x1. Why minus? Because I have given the force to the right, but the spring is bringing it to the left. I have to algebraically express this D'Alembert's principle. So, 2k x1 minus of k of x1 minus x2, which is minus 3k of x1 plus k of x2, okay. I bring it back here. So, m x1 double dot plus 3k x1 minus k x2 is 0, okay. I will write on the second equation here itself. So, it is easy for us to capture. So, for the second degree, f m x2 double dot will be minus of k of x2 minus x1. So, m x2 double dot minus k x1, because here it is positive, brings it here negative, plus k x2 is 0. Now, I got two equations, this is the first equation, the second equation. I can now write in the matrix form both the equations. Now, I want to ask you a question, is there anybody who is not able to understand how I am marking these arrow directions, how I am writing these values? We can repeat it very quickly again. I will not rewrite it again, I will write only the figure. I have a mass which is m indicated here. The mass is going to move to the right, but the spring will not allow the mass to move. Therefore, it is the force which is spring constant multiplied by only x1, that is the displacement. Whereas, this spring is connecting two displacements, and this spring, when you try to pull the mass towards right, the spring will compress the mass or push the mass towards left. Therefore, the direction is this way, k is the constant multiplied by the point where you are discussing is the first coordinate and then the second coordinate. Similarly, for the second case, I say m, pull the mass this way, but the spring will try to move. Now, the coordinate of the first and then the second. That is what we wrote here. We reassembled them and we got the equation. Now, this is the first equation, the second equation. I write them in matrix form. We already know how to write them in matrix form. So, m 0 0 m of x1 double dot x2 double dot, you can read it, mx1 double dot, that is the first term here, plus k, so 3k minus k of x1 x2 is set to 0. Let us read this matrix. mx1 double dot plus 3k x1 minus k x2 is 0. Similarly, mx double dot x2 double dot minus k x1 plus k x2 is 0, that is what I am having here. More interestingly, when your displacement coordinates are selected at the point where the mass is lumped, mass matrix will be always diagonal, the off diagonal elements will be 0, okay. And usually the stiffness matrix will be symmetric usually, and the stiffness matrix will be diagonally dominant. It means the values here on any row will be higher. So, these are some checks. If they are not diagonally dominant, you cannot take an inverse. Inverse of this is nothing but flexibility matrix. Okay? Therefore, flexibility matrix exists. That is why we get stiffness matrix here. So, I can easily derive the equation of motion in a minute for a given problem like this. So, I can keep on adding degrees of freedom, keep on writing equations of motion, keep on developing matrix method, and what people generally think is, so they actually follow a principle 2k k 3k minus k, k. So, if this is let us say 4k and 3k, they simply say 7k minus 3k minus 3k 3k. This is actually a blind method of following, do not do this. This may be right, may be wrong, okay? Do not do this. Always derive from the first principles, because arriving or deriving stiffness matrix itself is a menace in motion structures. I will show you in second module how the stiffness matrix cannot be derived as like this. It is a very tedious process. So, always use first principles to derive the equation of motion, and from that plug out stiffness matrix and mass matrix separately. Okay. Now, since damping is not there, the damping vector and the damping matrix is absent. If it is there, it will also be present. So, I have derived the equation of motion using Newton's method. I will also derive the equation of motion using energy method next class, and compare this, that I will get the same equation of motion whatever method I follow. Okay. So, in this class we summarized very quickly what are the different elemental stages of understanding the dynamic response of a single degree freedom system or spring mass system, starting from undamped free, damped free, undamped force, damped force, resonant vibration, response build up, response deformation factor, and dynamic amplification factor, estimating zeta from half power bandwidth method, and also deriving equations of motion for multi degree freedom system, explaining back what are degrees of freedom, what are restoration forces, how are the arrows marked, how are the coordinates fixed, and how do we write, how do we assemble, how do we check whether the matrix is okay. We have discussed all these things in this class. Any doubt you have, please post to NPTEL. Any appreciation you have, please post to NPTEL back. Thanks.